Hello, this is Dr. Phil Rosenkrantz with an introduction to safety engineering and management. It covers some fundamentals that will help you understand any situation or case a little bit better. Big question is, what are the major causes of accidents? There's three basic uh, types of causes of accidents. There's unsafe acts, unsafe conditions, and unsafe policies and procedures. I'm going to go through this and I think you'll begin to understand a little bit more about how to look at accidents. First, unsafe acts. Let me say that if you ask someone what's the cause of an accident, a lot of people will say carelessness. In the world of safety professionals, safety management, the word carelessness is not used because it's a cop out. There are reasons that people have accidents that are related to unsafe acts. So we're basically taking this word carelessness, throwing it out of our vocabulary, and replacing it with more helpful explanations. And these five do a pretty good job. So lack of knowledge is basically referring to a person not understanding what is considered to be safe in a particular situation. And and so that can be addressed with training and coaching and other things. Out of habit refers to when someone is out of their normal routine, sometimes they do something that is unsafe. Lack of incentive refers to people doing things that are unsafe, actually knowing that they're unsafe, but since there is no perceived punishment or uh, no this no expectation of getting in trouble, they do it anyway. A quick example would be uh, at the pool, or they have signs that say no running, but sometimes you see people running. Well, they know they're not supposed to run, but they run because they figure they can get away with it. If you're at a pool where if you're caught running and you get kicked out, you'll find there's a lot less running. The fourth one, procedure encouraged risk taking. This is where you're doing something where what you're required to do in some way actually encourages risk taking. An example I want to use here is, say, a driver that has a fixed amount of time to deliver packages might speed and take the risk of an accident or a speeding ticket because they're supposed to get things done in a certain way or a certain amount of time. And finally, physical condition. There could be hearing loss or vision issues that could lead to unsafe acts. Unsafe conditions can also be affected by situational factors such as defects in design, poor construction, improper storage of hazardous materials, and inadequate planning and layout. With respect to planning and layout, this word egress refers to the ability to exit in case of a fire or some other kind of problem. It could be a spill of some kind. And a lot of times there's poor planning for how people are going to exit. Another consideration are physical problems related to things like noise or vibration, or chemical issues related to fumes and vapors, and also biological hazards, um, bacteria and viruses. Let's talk about hazards next. A hazard is any existing or potential condition which by itself or interacting with some other factors can result in unwanted effects such as death, injuries, property damage, etc. And two common categories are injuries and illnesses. When we're talking about eliminating hazards or dealing with hazards, there's a nice model to look at, especially if you're doing any kind of engineering or design or problem solving. Look at a hazard as having three components: the source of the hazard, the path that the hazard takes to uh, toward a victim, and finally the receiver or victim of the hazard. So we're going to use this model to help us mitigate hazards. The number one most effective way to deal with hazards is at the source, and that is to eliminate the source if at all possible. If you eliminate the source, then the problem is solved. The next best way would be to reduce or minimize the source of the hazard if you can. So how do you do that? Well, if you're on the engineering side of things, you try to design the facilities and your products to be free of hazards to begin with. In the manufacturing arena, you want to design tools or do job hazard analyses to identify hazards so that you can change processes. In the area of quality, when you're ordering materials or testing designs, that's a nice area that you can look at for minimizing or reducing hazards. The purchasing department can be helpful too in making sure that they're getting material safety data sheets and only using approved materials. The maintenance department can help by maintaining things so that uh, different things don't fail ahead of time. And preventative maintenance is a bigger program now than it used to be. And also, industrial relations refers to having good training programs to make sure that people understand uh, how to eliminate hazards. Hazard control also recognizes that there's an interaction between people, equipment, the environment, and so you need to take all that into account, and also you need to take interpersonal relations into account. Uh, Dealing with people, making sure they understand, getting them on board, that's a factor. We've talked about eliminating the source of a hazard, but if you can't eliminate the source, then you want to interrupt the path that the source takes toward a victim. You can move the hazard farther away from where people are. You can enclose it or fence it in and put up guards. And those are things that you would do if you just can't eliminate the source or minimize it enough. Finally, if we can't do a lot about the source or the path, we have to protect the receiver, the person. And the way we do that is often by using personal protective equipment, or PPE. This could be aprons or coveralls, gloves, hard hats. There's all kinds of different forms of protective equipment. The reason we try to avoid this approach is because now you're in the area of having to provide the equipment, get people to use it properly, and get people to use it at all. Uh, Make sure that it's when it wears out, it's replaced. It costs a lot of money, so it's really not your first choice of dealing with a hazard. Then, as mentioned, you have to train people to use it, enforce the use of it, and so it's a least effective way. Let me just give one simple example. It's safety glasses. People should have safety glasses whenever they're inside of any kind of a factory where work is being done, and yet you don't always see that. Sometimes you'll see requirements for safety glasses, but you don't see it enforced. An example safety, of a safety situation that we've seen uh, in recent history have to do with nuclear power plants. And there's two notable power plant failures. And I'm not going to go into depth here. Those of you that are taking an ethics class will read about these in the chapter on safety. In the United States, the 3 Mile Island, TMI, nuclear power plant had a problem. And although no nuclear radiation escaped and there were no injuries, it did cause the meltdown of a unit that could never be used again. Um, so that's example number one, and it had a certain chain of events that you can study. The second one is Chernobyl in Russia, where they had a meltdown of a reactor, a complete meltdown. Radiation spread for hundreds of miles. People died and were victims of radiation for decades. Terrible situation. Whole different chain of events. Bottom line is we learned lessons from these. And in respect to 3 Mile Island, there was a huge sea change in the whole world of nuclear energy as far as how to operate, how to train people, and how to protect against having nuclear plant meltdowns in the future. It made a tremendous, resulted in a tremendous change in the approach to safety. When we talk about safety, sometimes you hear the word safety factor or margin of safety. These are useful terms to know. Let me use a bridge as an example of what we're talking about here. If you have a bridge that cars and people cross, you want it to be strong enough to hold the load of the weight of the cars and the people. So there's a couple of considerations here. You need to have some idea of what that load could be. Well, you're going to have an average load, which would be the load when the typical number of cars and people are on the bridge. But what you want to do is design the bridge so that it can handle the maximum expected load. So you have to estimate, if it was filled with cars and filled with people, what would that load be? And that would be kind of a design target, except that when you build the bridge according to your design, you don't always get the exact design that you planned for because of variation in materials and construction and workmanship. So you could have the same design but end up, say, if you built two bridges with that design, their actual working load wouldn't be identical. One would be higher working load than the other. Just the way the cement cured or welds were done or which products were used, etc., affect the true design load, or rather the true load compared to the design load. So how do you handle that? What you do is you actually plan your design to be higher capacity than your highest anticipated capacity, just in case the as-built bridge is not as high as what you targeted. So, how much do you over-design something so that you don't have a failure, a catastrophe down the road? And that's where these two terms come into play. In this particular graph, um, you'll figure, you'll see at the top, you see two distributions. Um, the one on the left is the distribution of the expected load. So the right tail of that curve would show what the maximum load is anticipated to be. On the right side, you see the design or expected load uh, in the center there, where it says letter C, and you're anticipating that there could be some variation for the as-built bridge. And so if you look to the left tail there, uh, you want that to be higher than what the maximum expected load is. That way you can avoid having a, uh, a failure of the bridge when you have happen to have the largest capacity on it. And the gap between those two numbers, the highest expected load and the least expected capability, is called the margin of safety. And so you want to build in some margin of safety. Now, how big should that be? Well, that's what engineers have to figure out, and they have to make sure that they have a large enough margin of safety to compensate for any mistakes they might have made in judgment or design or in even just understanding what the hazards are. So that's margin of safety. But sometimes we hear the term safety factor. And the safety factor is the ratio of the expected load to, um, rather, the expected design capability divided by the expected actual load. So if you wanted to use the numbers on the chart or letters on the chart, it would be C divided by D is the safety factor. Now, the safety factor only works if you also have a margin of safety. So for example, on the bottom figure, you see those two curves overlap, and there's an interval there where you're at risk of having a bridge built that can't handle the load, which could lead to a catastrophic failure. So the safety factor used all by itself only works if it is so big that you can't have any overlap in those two parts of those curves. The margin of safety, to me, is a better target because you know that those two tails don't overlap. But anyway, you can see what those two terms mean. Sorry I elaborated so much on those, but there seems to be a lack of understanding of what those mean. Well, now I want to talk about an incident versus an accident. An accident is when something goes wrong, but somebody gets hurt or killed, and there's property damage. And usually when there's an accident, because there's something usually tragic or expensive about it, people say, oh, how did that happen? They investigate and typically try to mitigate it in some way. An incident, on the other hand, is when something goes wrong, and it could be the exact same thing that happened during an accident. But in this case, by luck or happenstance, nobody got hurt or there was no property damage. And sometimes all that happens is people just put stuff back where it was. If something fell off a shelf, they just put it back up on the shelf. There was no loss in the case of an incident. But in the world of safety, incidents need to be investigated just as much as accidents because the next time somebody could get killed or hurt or something could be damaged. And so good safety programs keep track of incidents as well as accidents. And one way they do that is by auditing behaviors, where you actually go out, walk around, and observe what's going on, what people are doing, what material handling equipment, like forklifts, are doing, and and just look at behaviors and see if any are any unsafe behaviors around, um, so that you can avoid accidents in the future by whatever you need to do to mitigate it. So what you're really doing is you're looking for incidents so that you can work on preventing accidents. Now I want to end this um, video with a couple of examples of incidents and accidents. An incident example I have refers to an engineering intern that we had when I worked at General Motors in the industrial engineering department. We had an intern from a polytechnic university that's up in the northern part of the state of California. So I'm not going to mention the name of the university, but the initials are Cal Poly San Luis Obispo. Anyway, we had an intern, and the first incident that happened was um, he was out in the paint department and with a couple of other industrial engineers, and he happened to be uh, wearing really expensive clothes. In the factory, we tell everybody buy the cheapest shirts that you can buy, because things are going to get painted on, they're going to get cut by sharp objects, they're going to get sealer on them. You can't go a day without messing up clothing, so you buy cheap stuff. But he was wearing very expensive clothes. And even though he'd been warned, he wanted to be a clothes horse. So he got some sealer on his shirt, and he picked up a styrofoam cup, and he was going to dip it into a vat of solvent to get a little bit of it that he could use to wipe off the sealer with. And the engineer standing there next to him told him not to put the styrofoam cup into the vat of solvent. And he said, "Oh, I just need to get a little bit to clean my shirt off." And the engineer said, "Don't do that," because he saw that the cup was moving toward the solvent. And he kept warning him not to do it, but he ended up putting this cup in the solvent. Well, the solvent just ate the cup alive, and sizzled and popped, and the student had to yank his hand away so that he didn't get injured. And he got chastised for not listening. Well, move ahead. I was working with him, and we were in one part of the factory, and I needed to know how many bodies of cars were between me and another point in the plant. And the way I could get that is by sending him to that location, record what the job number was, and come back, and I could just subtract the job numbers, and I'd know how many cars were there. So he knew the location of where I wanted him to go get the number. So off he went. Well, he came back in a very short period of time, and I couldn't see any way that he could have gotten there and back in that short period of time. And I said, "Are you sure you went to the right place?" And he convinced me. Yeah, he says, "That's where I went." So I said, "All right, I don't know how you could have gotten there and back so fast, I want you to show me how you got there. And he said, okay. He said, I took a shortcut. And I said, what? He said, yeah. And I said, show me. What he had done was he had gone over to what we called the ELPO tank, electrophoretic paint deposition. It's a huge tank where we dipped car bodies into it, applied 475 volts of power so that uh, primer would attach to the car body. He had walked into the vat and using the small ledge that was across the vat for maintenance to use, he had crossed across this open vat to get to the other side. And by doing that, he actually created a huge shortcut for himself. Then he went and got the number and he came back and walked across the vat. Huge potential injury from something like that. So I called my boss and I said, come out here, I have to show you something. So I showed him what the student had done. And so what ended up happening was the student was restricted for the whole rest of his internship from going out on the production floor. He was restricted only to projects inside the IE office. Now my point there being is that nobody got hurt in those two situations, but you could see that he was in accident looking for a place to happen. And so wanted to share that. Now, while I was working for General Motors for 15 years, during those 15 years, at the plant I was at, we had 4 fatal accidents. Now, let me say that even one fatal accident in 15 years is considered bad. But 4 fatal accidents is a lot more than you would expect. I want to describe these to you, not in great detail, but just in enough so you get the idea. And then you can go back and ask yourself, were these the result of unsafe conditions, unsafe policies and procedures, unsafe acts? So let's take a look. The first one was a case of an electrician, and electricians often had to climb up into the overhead, up into the rafters of the plant to work on junction boxes and do their work. That's very common. But this one particular location in the plant had a span of a rafter, and these were all steel beams. And the practice that you were supposed to follow was when you're working on a junction box and you want to go to another one, you would climb down the ladder, move the ladder over to the next column, and then climb up. But sometimes electricians, instead of doing that, would just walk along the rafter, and because it was maybe 8 or 10 inches wide. They weren't supposed to do that, but a lot of times they said, oh, it saves me time, I can walk across. Well, one time an electrician was walking along and he fell and he landed on the hard ground and he died. He was supposed to move his ladder, but instead he walked across. The next incident had to do with a security guard, and this was at night, and out in the plant, out in the yard way in the back, a ditch had been dug to lay some kind of pipe or some other kind of utility. And normally, if you do something like that, you cover up those open trenches with boards or steel plate or something. But for some reason in this remote part of the plant, they left the ditch open. That's problem number one. At night, our security guards go on patrol and they drive around uh, throughout the plant, throughout the yards on scooters. The scooters are supposed to have governors on them so that they can't go more than 10 miles an hour. But sometimes what people would do is go in and they would remove the governor, and that way the scooter could go up to 25 miles an hour. Well, one night, trench was uncovered. A security guard drove through. He hit the trench going 25 miles an hour, flew off the scooter, hit his head, and died. The next incident had to do with material handling. Um, in the area where we stored racks of engines as they came off of rail cars, um, huge forklifts would carry these racks of engines, and what they would do is to put them into storage, they would often swing around a corner so that they could uh, uh, swing the rack into its location. They couldn't drive it straight in because they didn't have enough aisle space to do that. So you had to swing racks in. Well, if somebody is standing where that rack is supposed to go, they're in a blind spot to the driver because other racks are in the way. And so because of that, we have zones in the plant that are restricted and no pedestrians are allowed. Well, one day, for some reason, a very experienced material records uh, person, with 3 months to go before he was supposed to retire, um, was apparently over at a rack of engines for some reason, and a load of engines was being put there. The guy swung around and he dropped the load of engines, but he didn't even know the guy was there. And anyway, the shift ended, time passed, and nobody could figure out what happened to that one person who hadn't punched out. Well, anyway, a search ensued, and they found him dead between two engine racks. Well, of course, that really upset the person that was driving the engine, the forklift with the engines. He knew the guy that died, but nobody was supposed to be there. So why was he there is a question. Now the fourth death is the goriest, and so this is a warning. Um, we had a place where when the bodies would come up from the body shop after they were welded together, uh, they needed to go to the paint department. But before that, they needed to be cleaned, and solvents and dirt and everything like that needed to come off. So we had a station where operators could wipe off the bodies with some kind of a solvent, and then the body would go into a tunnel and go through a long acid bath where nozzles with acid would then totally clean off all the solvents from the body. And then when the body came out of that tunnel, it was ready to get primed and painted. Well, there was an operator who worked at the solvent wiping operation, and he was a druggie. Everybody knew he was a druggie. Um, his father worked at the plant, had been there a long time, and everybody loved his father, so they were tolerating his son. And his son would do kind of goofy things. But one of the things he used to do was threaten that he was going to get into the trunk of the car and go through the acid bath. And he would joke around. Well, one time he apparently got in the trunk and it locked on him. He was probably inside the beginning of the tunnel. He couldn't get out. Nobody could see it. And he went through the acid uh, bath and died a horrible death. As soon as his coworkers realized that his he didn't come out of this tunnel or whatever, they shut the thing off. They got maintenance there. They went in and they found his body. Um, so that was just awful, and it wasn't just awful for the person that died and for his family, but it was awful for those that had to pull his body out of this uh, trunk of this vehicle. So anyway, those four incidents, I'm saying that because um, I want you to think about why did those happen. And in fact, I'm going to probably use these for discussion purposes. So thank you. I think that's all I have here. And I hope it helped give you some kind of a understanding of some of the basic concepts when it comes to safety.